So in the last video, we introduced the power of memory coalescing, but sometimes it's very hard to access the data in a coalesced way. A very good example is matrix transpose, because on one side we need to access data horizontally and on the other side we need to access the data vertically. So there must be one time that where memory access is not coalesced. So in this example, let's see how to utilize LDS to convert non-coalesceable memory access to a coalesceable memory access. So first, let's look at the naive memory access implementation. In this implementation, we have a transpose kernel. We implement as a template function, but you can consider it just as a single precision floating point number. We have an in, out, width, and height, which are very standard for matrices. The width and height describe the input matrix, and the output matrix will have the reversed size. We first calculate x index and y index. Here we're using a two-dimensional kernel. And if the x index and y index is within the range, we calculate the input index and output index, and assign the input to the output element. So we can profile this program and see what's the performance. So we use this command rocprof heap trace stats main to get the execution time of the kernel. And we also use this matrix.txt as the input to rocprof to profile the kernel execution. So as we profile the program, we measure the write size and fetch size, and they're both in the unit of kilobytes. As you can see, here we're writing 3 gigabytes of data and reading 1 gigabyte of data. And the matrix we're using is 16K by 16K. So if we calculate the size, it's only 1 gigabyte in size. So the read size is reasonable. We read a little bit extra, less than 1%. But the write size is not right. We're writing 3 times more data. The problem is that our read access is coalesced, but our writes are not coalesced. So we have to perform a lot of redundant writes, and that causes slowdown. So let's try to analyze this program in a graphical way. We have a main input matrix on the left, and we have an output matrix on the right. We need to move data from the left to the right. We load data in this way. We load these 4 orange boxes into the 4 blue boxes. As you can see, both matrices are row major. So when we read the data, adjacent threads are accessing adjacent data. So when we write the data, adjacent threads are writing data that are very far apart. As we keep going on, every access is the same. The read is coalesceable and the write is not coalesceable. So the question is there a way that we can enjoy both the coalesced read and also convert the write into a coalesceable write? So luckily we have LDS as an intermediate point. We can first load the data into LDS in a coalesceable way, and then we can write the data from the LDS in a coalesceable way. So let's look at the solution in the figure first. Assuming we have an LDS and we have a tile of the matrix. This is not the full matrix, it's just a small region of the matrix. It can be something like 8 to 8, 16 by 16, or 32 by 32, but typically it cannot be larger. This is limited by LDS size. As we load data, we load first the row and we write into LDS. Remember, only reading and writing the main memory will have coalesceable effect. LDS is implemented in SRAM, so it's not cached, so there's no coalesceable effect. Accessing any element in LDS is fast. So we can load the data from the main memory in a coalesced way and writing the data into LDS. And we load all the data into LDS, row by row. And at this moment, we have all the data in LDS. So we want to write the data into the output matrix still in a coalesceable way and still row by row. But here we need to perform a transpose operation. So we can read the first column in LDS. It may look like a non-coalesceable way, but remember, accessing LDS is really fast and there's no problem with coalescing. So reading a column of data in LDS has no performance penalty. But when we write the data horizontally into the output matrix, we can still coalesce the output. And we can keep doing this operation until we fill all the output cells, and all the write operation to the main memory are coalesceable. So by using LDS as an intermediate stage, we can both enjoy coalesced read and coalesced write. And this mechanism is called tiling. So let's look at how this tiling-based mechanism is implemented in code. So here is the code of the tiling-based transpose. The input and output are the same. Here, just for simplicity, we use floating point numbers. We first allocate a chunk of LDS memory named tile. It's a two-dimensional array. These tile-dim variables are defined as a global variable. And then we calculate the index within the tile. We have a X tile index, Y tile index, and the tile size is identical to a block size in both X dimension and Y dimension. And here we set the X dimension to be the same as the Y dimension so that we can have a square tile. Then we calculate the input index. It's a little bit more complex, but it's still basically the same idea. We calculate the input index and output index. The calculation is a little bit complex, but if you consider elements within the parentheses as one bigger element, then it's basically the same way as calculating input index and output index in our naive implementation. And in the third line from bottom, we load the data from the input matrix to the shared memory. Now here, we need to do synchronization. We have to guarantee all the wavefront have loaded the data so that we can write the data into the output matrix. And finally, in the last line of this kernel, we load the data from the tile, from the shared memory, and write it into the output matrix. So be careful here, these tile indices are different. The first time Y is in the front and X is later. And the next time X is in the front and Y is later. So that basically means for each thread, other than the threads on the diagonal line, it's writing to the LDS one piece of data and reading another piece of data from LDS and writing into main memory.